So section 2, why GPU computing and how to program GPUs. Okay, if you read this title, it's simple. In this section, we have two questions to answer, the why and the how. Before we move forward, just some copyright disclaimer. Is that the fact is that through this set of slides, I have used a lot of material coming from the internet, and each time I did that, I put the links at the bottom of the slide to show where is the source of the content and who is the owner of the copyright. Okay, in this section, we are going to touch the first point is that data parallelism. The second one is how to offload workload to the GPUs. The first is why, the second is how, and the third one is here to point out that there are many, many ways to offload the workload to the GPUs on the marketplace. Okay, parallelism. We need to have a historical view of the history, the computing history. So the first thing we need to have a look is the vector systems. So Seymour Cray, the famous Mr. Seymour Cray, which is his name right now is the name of the Cray computer. Himself, Mr. Seymour Cray designed totally 3 vector systems, the Cray 1, 2, and 3. Cray 1 was announced in 1975. The Cray 1 vector processor had 8 times 64 times 64-bit vector registers to explore data parallelism by using the vectorization. So really, this is the starting point of the HPC industry. And here in the middle, what we have is the microarchitecture of the Cray vector processor. You have vector register 0, 1 up to V7. So you have 8 vector registers. And you have 8 vector registers. And each register, you have 64 times 64-bit. Okay, just remember that each 64-bit is a floating point. Is a double precision floating point, double precision. And this is the standard for the science and the technical computing, because we need to have a floating point with 64 bits. FP64 is the working horse for the HPC industry for science and technical computing. Okay, so what we can understand is that the Cray started the way with vectorization to explore the data parallelism. That means you need to have lots of dates, and you are processing the dates in parallel to give the performance, to deliver to the industry performance. And for that reason, we know we have 8 vector registers, and each one is 64 times 64 bits, and each 64 bits is a floating point. Okay, and we can see if you look at that in the details, you can see we have these functional units, vector functional units, and floating point functional units, and we have these scalar functional units and address functional units, okay, etc., etc. Okay, since the beginning, from the 1970s up to the beginning of 2000, roughly 30 years. For 30 years, for 30 years, we have these vector machines on the marketplace. So it's kind of history, is kind of legend. I mean, you have these kind of vector systems dominate the system, the marketplace for the let's say for the beginning for the first 2 decades, and then faded out in the last decade. So roughly 30 years. That's is kind of legend. So this is the history, and right now, pretty much people is saying that vector is died or is dying, because right now the only vector product you can find from the marketplace is the vector engine. It's called vector engine from NEC. That's what we can find. So I'll be saying that it's dying, it's not totally died yet. And then there is a new trend, is that RISC-V, they have deployed, no, not deployed, they have reinvented this vector extension for their RISC-V CPU. So right now, there are vendors, they have already built the vector extension for the RISC-V CPUs. You can find these kind of products from the marketplace, but the fact is that it's not the mainstream yet. So I'm happy to say that someone like me, they don't like the fact that the vector technology is dead or is dying. So they would like to reinvent the vector machines, the vector extension, the vector technology. So there are people are doing that. Okay, so the vector systems, to deliver this performance to the industry, the vector systems, they have explored the data parallelism. So parallelism and the data parallelism. That's what happened starting from 1970s to roughly 2000. Okay, we move to the second part, parallelism. The second part is that modern superscalar CPU, notably the x86, explored instruction level parallelism up to, let's say, up to 2000, let's say 17. Okay. What we can say that starting from 80s, we start to have this kind of booming of these x86. So started from roughly, I'll say that started from late 80s, 90s, we started to have this booming of the x86 based systems, started from the PC and later on to the server market. Up to now, they are dominating the server market and also this HPC market. But if you remember at the beginning from the 90s, for let's see, for a decade or a decade or so, or 2 decades, there are the performance of the x86, they are based on the instruction level parallelism. So at the beginning, the x86 CPUs, the x86 processors, they have explored instruction level parallelism. Okay, so that was instruction level parallelism. Sorry. Instruction level parallelism, ILP, allows multiple instructions to be processed concurrently within a CPU. So you have instructions. Normally, you are going to execute the instructions one by one. in a series. But here is that the CPU, they have a bigger window to say a number of instructions. They are going to decide these instructions whether they can be executed at the same time or not. If can be done at the same time, that means you have a kind of instruction level parallelism there, and they are trying to explore this kind of parallelism, instruction level parallelism. The techniques used was pipelining, superscalar execution, and out-of-order executions. Okay. This had happened within roughly 2 decades. And if you remember, at that time, they have explored this instruction level parallelism, and at the same time, they also increased the frequency of the CPU from megahertz to gigahertz to a few gigahertz. Now, that's kind of, you have a kind of a performance increase. But the fact is that instruction level parallelism is not enough to deliver the performance required by the industry. So it's not enough. So started from 2017 with the Skylake, with AVX 512, x86 started to explore data parallelism by using the register-based single instruction multiple data. Okay, so I have got this microarchitecture of the this is not this Skylake. I think this is I'm a little bit lost. I'm not sure this golden curve core is the Skylake. Maybe this golden curve core is the Skylake. And let's try to find out where is this SMD. Pretty much, I think here is FMA 512. This should be the functional units that are used to explore the data parallelism, mainly SIMD. Okay, but what's SIMD? Now, that's very simple. You have 2 vectors, x and y. You want to do a sum of the x plus y element wise. So you want to have x7 plus y7, and in the result you have the sum of x7 y7 here. So this is the mathematics. The way for x86 to do that is you have hardware units. So here, what we have is this AVX 512 means you have 8 hardware units. Now, you basically you have the AVX 500 means that you can do 8 64-bit operations at the same time. So you have one instruction. The instruction is you give the unit an instruction is that you do the sum. You do the sum of x plus y. This is instruction, and you have only one instruction. And the fact is that you have 2 vectors. Each one you have 8 elements, and each element is 64 bits. 64 bits is a floating point. 64 bits. Floating point. So you have 8 hardware units that's going to do the sum of the 8 elements at the same time. So single instruction, multiple data. Multiple data means you have multiple elements, and the final result will be put in x plus y. So instruction multi-data, this is the meaning. And to do that, what you need to do is that you need to have the hardware functional units, which has multiple functional units. And each functional unit is going to execute the same instruction, but each function unit is going to execute on different data. So this is called single instruction multiple data. We just need to come back to the fact that here you have AVX 512. That means you have 512 bits. That's 8 times 64 bits. But if we come back to the Cray system, each vector register is already 64 times 64 bits. So each vector register is already 8 times bigger than the AVX 512. Plus the fact you have 8 vector registers. So you can do much more. You can do much more than AVX 512. That explains the vectorization system created by Cray. It has the possibility to explore more data parallelism than the AVX 512. But AVX 512 really starting from 2017, the x86 systems, they also started to explore the data parallelism because this is the way to go to deliver the performance required, demanded by the industry. There is no other way. You have to explore the data parallelism to deliver the performance, ever demanding performance. Okay, this is x86. Right now, if you look at this ARM processor, it's getting popular. ARM processor has a similar SMD extension is called SVE, Scalable Vector Extension. Basically, it's the same thing as AVX 512. Now it is in its version 2. Okay, so the started from 2017 up to now. We have noticed that x86 also started to explore the data parallelism to deliver the performance to the industry. Okay, now we move to GPUs. GPU computing falls in the broad SIMD category. Okay, GPU basically the GPU systems. If you do the classification of the computing systems, the GPU should be classified as SMD computing systems, but it's technically is a little bit different. Is Nvidia call their GPU computing system using the single instruction multiple threads technology. Okay, so at the end, the fact is that this SIMT is exploring the data parallelism. Okay, so starting from the first day, it starts to explore the data parallelism. So it's in the right direction to delivering the performance to the industry. You have to explore data parallelism, and start from day one. The GPUs are doing the same, the data parallelism. The technology is called single instruction multiple threads. Basically, conceptually, it's the same thing as single instruction multiple data. Conceptually, that's the same, but we are going to find out that because the fact that you have so much threads, so Nvidia is calling this kind of technology SMT. But anyway, we are going to find that out. So let's have a look at this GPU from Nvidia. It has 132 SMs, and each SM is like this. it has 4 identical units, and each unit you have 16 FP64 units. So we can do a math. You have 132 SMs, and each SM you have 4 identical units, and each unit you have 16. So that means you have floating points, 64. That means each GPU you have the possibility to do the calculations at the same time. This is the calculations can be done by by a GPU. Let me do a calculation. That's 132 multiplied by 4 by 16. So you have 8,000. Basically, you have 8,448 units, hardware units. Is hardware FP64 units. So that's quite a lot. So you have, if we come back and think about the basic concept of single instruction, multiple data, or single instruction, multiple threads. So I have a single instruction. I'm going to have 8,448 threads. I give one instruction to threads. The threads could be executed on 8,448 hardware units. So at least if I have only one thread per hardware unit, we can do 8,448 executions per instruction. So that's the basic idea of data parallelism. Starting from day one, is doing that like this. But there is there is something I have to mention is that the fact is that to make full usage. Let me have a look at the next page. Not in the next page. Okay, so the fact is that the what we know that the why the for GPU is not called a single instruction multiple data, but instead is called instruction multiple threads, because the fact is that for the GPUs they are doing basically is Nvidia and AMD is claiming they are doing thread computing. The fact is that with GPUs, you can switch from one thread to the other at one slot, very, very quick. So basically means that 8,448 hardware units, you can run at the same time much more than 8,448 threads. We know for CPU computing, usually what we are going to do is that we are going to have one thread per hardware core. But here, you can have much more than one per hardware unit for the calculation. Much more than one thread than the hardware units. So that means we can run much more threads per hardware unit. Now, we can claim that minimum we need to have 1 million, roughly 1 million threads to use a GPU to be to work with the data transfer from the CPU to the GPU. So if we do 1 million threads, 1 million threads divided by the hardware units, so That means we need to have roughly, we are going to have roughly 100, let's see, 100, no, sorry, 128, something like this, threads can be run uh, per hardware unit. Okay, so we won't dive into too much in these technical details. The fact is that here we have a look here. It's called warp scheduler. It's called warp scheduler. It's called warp scheduler, and the warp scheduler can do is that it can schedule 32 threads to be executed on all these subdivision of the SM in just one clock. So 32 threads in one, to be 32 threads will be executed on this subdivision, and then next clock, it could be swapped to another 32 threads. So basically, you can have much more threads than the hardware units. We are talking about 32. Then basically, what I'm trying to say is that you can have a multiple of 32 threads per hardware units. Basically, what I'm saying is I have taken this number 128, which is four, uh, four warps. So, so 4 warps per hardware unit. So if you have this kind of GPU, if you have this is the floating point units you have. What we can do is that you can have multiple warps, multiple 32 times threads per subdivision of this GPU. And in the total, you can calculate, you are going to, what you need to do is to have around 1 million threads or more than 1 million threads to make it worth doing. But later on, we are going to find out that GPU computing is not easy. If you want to do GPU computing, the fact is that you have to really explore the data parallelism by having much more threads per GPU to make it worth doing, to make it worth your effort to move to GPU computing. Okay, so uh, the fact is that starting day one, um, uh, GPUs are exploring the data parallelism. We talked about this Nvidia GPU. For AMD, it's the same thing. It's the same story. So AMD CDNA architecture is their GPU architecture. If you look at the two GPUs in more detail, that's very similar. Just the two vendors are using different terminology, but anyway, it's quite similar. For example, we talked about these warp scheduler, and you have warps, but in AMD, the warp is not called warp, it's called wavefront. So it's really the same thing. Again, is to explore the data parallelism by using the SMT. So basically, the two is the same thing. Is using the SMT technology to explore the data parallelism to deliver the performance to the industry. And we have just a very quick look of this AMD GPU, is that in AMD you don't have the SM stream processor, stream multiprocessor. What you have is called CU. CU is compute unit, and you have lots compute units. And within each compute unit, you have, for example, here you have 4 times 16 wide SMD per CU for total of 64 shader cores per CU. So you have 64 shader cores per CU for floating point. And here it is. You have the first one is here, the linear one, and on the top you have another one. So the first one, the second one, and the third one, the fourth one. You have SMD units. Okay, so you have these SMD units per CU, 4 times 16 SMD units per CU. Then 4 times 16 wide SMD units. So you have per CU, you have 64 floating point, 64 capabilities multiplied by the quantity of CUs. How many CUs do we have? 1 is 2, is 3, 6, 9, 10, is 4. 4 divided 2 is, and totally we have 28 multiply 28 multiplied 28, sorry, 28 multiply by 4 and by 64 floating 64 bit floating point units, and the floating point units you are going to have is 64 multiplied by 28 by 4, and the fact is that you have 7,168 floating point 64 units. Okay. Now we know that we calculate for NVIDIA GPU is 8,000, for AMD CPU GPU is 7,000 floating point 64 units. And that's the hardware units. If you have more than 1 million threads, that means you have much more threads per hardware unit to execute. So and then that's the way to explore the data parallelism. Now, just to compare with the CPU, for the CPU to have the parallelism, what you are going to do is that you can have, and pretty much most of the time, you are going to have one thread per CPU core. And then you are going to try to explore the data parallelism by have by a by a lower quantity of number of threads, because if you are using a node, if you have 128 cores per node, if you have 1,000 nodes, the total quantity of threads you can have is 128,000 threads. So if you have 128 nodes, sorry, you have 128 threads. 128 threads, you have nodes, you have nodes is 1,000. You are going to have 128,000 threads to explore the data parallelism for CPU computing. But for GPU computing, just try to put that in your mind. Each GPU, you need to have around 1 million threads. To explore the data parallelism. Okay, so this is pretty much the a historic view of the industry. From this review, what we can understand is that to deliver the required performance to the industry, data parallelism is necessary. Everybody has to explore data parallelism to deliver the performance to the industry. Started with the vector processor, it has explored the data parallelism to deliver the performance to the industry. So for 30 years, it has been in the market for around 3 decades. And later on, we start to have these x86 systems around 2017. It also moved to the SMD technology to explore the data parallelism to deliver the performance to the industry. And later on, we have this GPU starting from their day one, they have started to explore the data parallelism to deliver the performance to industry. So from this very simple historical view, the conclusion we can draw is that the data parallelism is the must-have to deliver the performance to the industry. So this is the reason why we need to do GPU computing, because GPU computing is exploring the data parallelism, and that's the way to deliver the performance to the industry. Okay, so right now, if you look at the marketplace, what we have is the traditional computing with CPUs. It is exploring data parallelism, and we have this emerging, evolving GPU computing, and it is exploring the data parallelism it is exploring the data parallelism to deliver the performance to the industry. This is the facts. So that explains why we need to do GPU computing, because that's in the right direction. That is explore the data parallelism to deliver the performance. So we are going to have a rest. The second part, we are going to have a look how we can use the GPU to do the computing.